So first I should say that I'm working in medical imaging. And the idea is we're extracting lots of geometric features.
Oh, sorry, I did it.
Okay. We're extracting lots of geometric features, so it could be surfaces, it could be tensors, it could be deformations, and we want to do statistics on these features. And obviously, the first thing we are doing is computing mean values, but then we'd like to do a bit more, like something like PCA or decomposition or subspaces in which live the data, and it could be not just unimodal. So the data live on non-Euclidean manifolds, and we know that structure. Now, the idea is if we want to learn something, so if you take a space of surfaces or space of brain images, what we'd like to do is to do manifold reduction, to have just a few coordinates with which we could work. But at the same time, we don't want to just do standard manifold learning, put everything in a Hilbert space. I mean, we have already a structure. If we have transformations, they belong to a Lie group. We might have a metric, a Riemannian metric on the embedding space. So what we'd like to do is sub-manifold learning. So that's the motivation of this work. So the talk will be just first part, which is just recalling what is already known or done. And then I'm going to present in the second part the idea of the barycentric subspaces and the Affine span. OK, so just to set up the notation, I'm going to use geodesically complete Riemannian manifolds. And I'm going to use the expand log operation. So I guess that at that stage of the conference, I don't need to really explain what it is. The idea is we're going to reformulate everything with this expand log. And this is also my notation for the log, which is the vector that allows to shoot from x bar here to z. So if we are on a manifold, the idea to, well, there are several definitions of the mean value. So the easiest one that we're using, most of us, is the Fréchet mean. So we compute the variance, which is the expectation of the distance, and that's a function on the manifold. And if we look for the absolute minimum, that's what we call the Fréchet mean. Now, if we simplify a little bit the domain to try to, or the problem to try to characterize, then we can take the local minima, and that's what we call abusively the Karcher mean. So in this talk, Karcher is local, Fréchet is global. And then I'm introducing here just two notations, which are the tensor moments. So my way of seeing the moments of a distribution on a manifold is not just, these are tensor fields. So we can compute that at any point. So if we compute the tangent mean field, it's a tensor field whose 0 will correspond to the critical point of the variance. And we can compute the covariance field, which is the covariance of the data seen from any point. And these are living in tensor field of the manifold. And so the result is that so the variance is differentiable if we have density, and we can compute the first moment. And the idea is, well, the critical point of the variance are exponential barycenter, meaning that if we are at an exponential barycenter, then when we look at the data point, the mean is 0. Okay, but we can have minima, we can have saddle points, we can have maxima. Okay, so there's a hierarchy: Fréchet, Karcher, exponential barycenters. Okay, so now when we are at the mean point, usually we compute the covariance matrix, which is the value of the covariance matrix field at the mean point, and that's usually what we call the covariance matrix. And now if we want to analyze, well, the data that we have, the simplest we can do is tangent PCA. So we compute the mean, we unfold the data in the tangent space, we compute the covariance matrix in that tangent space, and now everything's linear, we can do PCA, take a few components of the PCA, and then pretend that this is our analysis of the data. So it corresponds to a model which is basically a Gaussian model for what is left out. So we are trying to minimize, well, somehow with this system, we are maximizing what is explained by the subspace or that we're generating. But we have, an implicit definition or an implicit assumption of a Gaussian distribution in the subspace and also out of the subspace. So we can try to minimize, well, there's two ways. We can either try to optimize what is explained in the subspace or minimize what is unexplained in the orthogonal space. But since we are in the tangent space at the mean point, this is roughly the same. Now, if we just try to generalize that and say, okay, we don't want to do the Gaussian assumption in the subspace, we can try to say, okay, with 1 point and tangent vectors, we can generate a subspace and generate geodesics. So that's what is called the geodesic subspaces. And now we can try to fit the parameters of this geodesic subspace to minimize the unexplained variance. So that is the original idea of principal geodesic analysis. I should just say that originally that was the idea, but it was difficult. So at the end of Tom Fletcher's paper, they came out to do tangent PCA. And Stefan Sommer did it correctly with all the equations a few years later. So then there are extensions, which is geodesic PCA. The idea is not to start from the mean, but to start from one geodesic and then iteratively add other geodesic components. And in that case, we end up with a generative model, which is making no assumption in the subspace that we are trying to estimate, but we are still minimizing the unexplained variance, so we still have somehow the idea that there is a Gaussian noise in the vertical space. So in a manifold, obviously all the definitions do not correspond because we minimizing or maximizing the explained variance is not the same thing as minimizing the unexplained variance, which is the case in Euclidean spaces. Okay, so the problems that we can have, so I stole some of the slides of Stefan from 2 years ago, because that's a good explanation. If you take this type of distribution on the sphere, well, you see that the mean value is there, and it's not part of the data. So the fact that we start with the mean value might be a problem, especially if we have multimodal distribution. Then we might have, like on the donut here, the mean value will be always a bad approximation of what you're trying to do. So if we have also a large variance with respect to the curvature, then we might expect to have some problems. So this is, in that case, what can we do? Well, the first thing is improve the flexibility of the geodesics, so going to higher order curves like splines. So that's, there are a few examples like that, but for 1D it's okay, but then if we're going to ND polynomials on manifolds, then it's quite difficult to control the number of degrees of freedom that we're introducing here. There's a second idea which is very interesting, which is the idea of having nested subspaces to do the approximation, and that can be done on the sphere. I mean, if you take a high-dimensional sphere, you can slice it, and you still have a sphere, and you can reslice it, and you still have a sphere. And all these spaces are embedded. And this can be generalized to quotient of Lie group actions. And this notion is very interesting, but it's exploiting the semi-direct product space structure. And in general manifolds, there's no reason why there should be such a structure. If there is one, I agree we should use it. But if there's no structure, what can we do? So we can do other stuff like horizontal frame bundle development or the stochastic PCA. What I would say here, the idea is intrinsically, while in horizontal frame development, the idea is first find one component, and then once this is found, find the second one. So it's intrinsically, there is an asymmetry between the different components that we get. And that's the thing that I would like to remove. What I would like to have is something which is parameterized, all the parameters being equally important in a subspace. Okay, so let's go back to what is an affine subspace in a Euclidean space. So we can write it with the above equation. So that's a point plus vectors belonging to a certain family, the span of several vectors. We can rewrite that in different ways, and we can end up with this type of equation where you see that this is the set of points such that they are weighted barycenters of vectors. Well, that is an equation that's ring a bell, because it seems that weighted barycenters or tangent vectors could be something interesting. So the idea is really to define these spaces as the locus of points, which will be the barycenter of a fixed number of points. From the previous idea was we stand up at the mean, and then we look at the data points Here the idea is the reverse. We stand at the data points and look at the mean. Or we stand at a point and look at the different reference points. And if we are in the barycentric subspace, then there will be weights such that we can see this point as an exponential barycenter. So that's the implicit definition of the barycentric coordinates that we will generalize to manifolds. So I need a few notations for that. The first thing is, so I'm going to take k plus 1 reference points. And at the cut locus of these points, then the distance or the log the log is not well defined. The distance is continuous but not differentiable. So we need to just, what I call the k plus 1 pointed manifold is the manifold where we remove the cut locus of the reference points. And then on this pointed manifold, everything is smooth, and we can work with that. In particular, we can define the tensor moments. So the first one is the density, and that's what we're going to use to, well, usually we take the sum of the lambda I equal 1, so we can just renormalize. Then we have the tangent mean and the covariance mean, but now they are weighted. So there's an additional variable, lambda, which belongs to a projective space. And that's a dual, some kind of dual coordinates to the point within the manifold. Okay, so whatever lambda, all these are smooth tensor field on the pointed manifold. And now we can try to define what we call the barycentric subspaces. So what I said is we have 3 definitions of the mean value. So we can start with the Fréchet mean. So we define the normalized, well, the weighted variance as the sum of the weighted square distance, and we just normalize it. And then we say that the set of the absolute or local minima of this criterion for some lambda, for any lambda that we want, that does not sum up to 1, is the Karcher or the Fréchet or the Karcher barycentric subspace. So this is obtained by minimization. Now we can also take the exponential barycenter definition. We can, and that corresponds to find all the point x such that there exists lambda such that the sum of the lambda I and the sum of the log to the reference point is equal to 0. And so this is what I call, so here I should say that I change a few definitions with respect to the paper, because it's in the paper this what called the affine span. Now this is called the exponential barycentric subspace, and I'm adding a new definition, which is the affine span is the closure of the exponential barycentric subspace in the manifold. So why is that? Because if we take that, we can recover the points which are on the cut locus, and when we take the example on the sphere, it allows to find back again great subspheres without any hole. And so it's kind of interesting to see that we have to go to exclude points for doing the differential calculus thing, but then taking the closure seems to reconnect what needs to be reconnected maybe at some point. But I don't know exactly what's happening. It just seems that this definition is more suitable. Okay. So now if we try to analyze what's happening, we can do as exactly following the idea of Karcher. We can analyze the Fréchet mean as local. I mean, if we are in a sufficiently small domain, then we can, well, obviously the local minima are, the global minima are local minimum. So the Fréchet barycentric subspace is a subset of the Karcher barycentric subspace. Now on the pointed manifold, the exponential barycenter, we see that they are critical point of the weighted variance. So we have this inclusion on the right. And then if we want to go one step further, we need to compute the Hessian. And the Hessian, we have well, Taylor expansion here. And what is appearing is this term here, which is actually the contraction of the Ricci tensor with the covariance matrix. So it's actually some kind of coarse curvature, but between quote. It's just that instead of averaging the Ricci tensor on all directions equally, then we're going to weight by the covariance matrix. And this is a term that we find in all the Taylor expansion that we can do on manifolds. So it seems to be one very important point. Okay, now this Hessian matrix, I don't know exactly how it is, but we can look at the points where it's degenerated. And at this point, if it's positively finite, then it is a minimum. So what we can say is the Karcher barycentric subspace is the exponential barycentric subspace, which is regular and where the point, this Hessian matrix is positively finite. So, and then we could add potentially some points of the affine span or some points of the cut locus. So there might be things just around on the boundary. Okay, now what's interesting is that the exponential barycentric subspace, we can rewrite them to try to characterize what is the equation that they are fulfilling. And if we write the first order moment as an equation, we just take at a point the log to all the reference points, and we put that in a matrix that I call Z. And this matrix, if I multiply it on the right by lambda, which is a k+1 vector, when it's equal to 0, it's exactly corresponding to the first moment, which is 0. So the equation is, we know that a point is in an exponential barycentric subspace if it's in the kernel in the left kernel of that matrix D. So we can do an SVD decomposition. And if the last, if we order the eigenvalue, if the last eigenvalue is 0, then we know that we are on the exponential barycentric subspace. And what we can see is that this is, if the Hessian matrix is invertible, so we should be at a regular point, then we can have a local parametrization, and it means that we can characterize the dimension. And the dimension of the manifold that we're generating, of the exponential barycentric subspace, is the dimension of the non-zero singular values. So it could be k with k+1 points. In general, it is k, but then it could be also k-1, k-2. So we got a stratification here. And we have the characterization that we have k-m+1 vanishing singular value on the m-dimensional strata. So it's more or less what's the same thing as is happening as in Euclidean spaces. It's just the setting is a bit more complex. And we can also characterize it with the Courant matrix or the Gram matrix. So we can build the Gram matrix, diagonalize that, and look at the eigenvalues. Or we can compute the Courant matrix, diagonalize it, and look at the eigenvalues. So it's exactly the same type of characterization as we have for the standard PCA. Okay, so just an example. 1 minute, okay. An example on the sphere. So if on the sphere, the cut locus are the antipodal points, so we need to exclude them for doing the analysis. And we find that exponential barycentric subspace are almost great subsphere, except the antipodal points. And the affine span, taking the completion, reconnects that in a single great subsphere. And what's interesting is that if we take the exponential barycentric subspace, we have the whole great subsphere. If we take the Fréchet or the Karcher exponential barycentric subspace, we have a strictly smaller set. And this set is depending on the position of the points. So it seems that the affine span is more generic than the Fréchet or the Karcher mean in this definition. So we can also take limits, and what we can show is that when the points are converging to one point at the first order, then what's happening is we're generating the subspace that we're generating is converging towards the geodesic subspaces that were used in principal geodesic analysis. So that's in that sense, principal geodesic analysis is a limit case of these barycentric subspaces. And on the sphere, if we take a second order convergence of the point, then this is converging to principal nested spheres. And the conjecture is that this could be generalized to higher order jets. So I think I'm finished with that. Last question is, well, we use the Fréchet mean, the expectation of the square distance. Can we change that for a D mean? Well, we can probably do something more robust. Well, the answer is no. The affine span is exactly the same. So a weighted mean is also a weighted median, but with different weights. So that's time to finish, yes.
Okay, thank you very much.
So questions?
You said. Thank you for this very nice talk. So I'm sure that there is some question in the audience. Yeah?
Could you indicate, for instance, by one example, how this your new stuff can be applied to the topics indicated in your first 2 or 3 slides in neuroimaging?
Yeah, so there are several ideas. So the idea is to optimize what are the points, and then what we need is to set up also the projection of the points on this barycentric subspaces. So there's algorithm to develop. So they are currently under development. The first idea was to try to push what is the is it a correct subspace to work with? And it turns out that it's much better than what I expected at the beginning. It seems to be, well, there seems to be much more properties, and especially for the idea of computing the mean. I mean, if we're going to the weighted mean, then it's waiving lots of the problem that we had with fixed weights. So now to just one example, I think I've got one there, which is, we started with that. It's in image registration, and the idea is if we have registration from frame to frame in the cardiac sequence, then we can choose reference images, and we can compute what are the deformation from each image to the reference image. And this is giving weights, so we can also optimize what are the reference image that we use in that sequence to have the minimal error. And if we optimize to do that, then we end up with this type of curves. And here it's just an example with healthy and diseased hurt. And it seems that, so a straight line in there would be somehow geodesic. And it seems that the healthy are more geodesic, at least on some of the cardiac sequences. So that's just very rough stuff, but it seems that it's already a very good approximation with only 3, well, actually here, 2 degrees of freedom, because it's homogeneous.
Okay, so maybe, yes?
Yes. Yeah, and that's important, because if we restrict to positivity, then we restrict to some kind of, we want to have well, we can have something which is, if we are in the condition of, if the reference points are sufficiently close, so on the sphere it should be the upper hemisphere, for instance, so that's the condition of Kendall theorem, then you have something which is convex, and you can define stuff, but you also have a set of positive weights on the other side that are shooting also to the reference points with much larger weights. So, and this is something that, I mean, you can, it's very difficult with to work with that. If you just think that you can have positive or negative, you can just go a little bit away from the reference points. You can go farther away than the reference points. Now the good constraint is rather to have lambda less than 1, and not between 0 and 1. Because in that case, you're trying to find what is the archetype, what is the extremum that you can reach, and then the other one will be, well, the weight will go down, but you can go on the direction, and you're trying to contain your data in the space which is generated by archetypes. And that's interesting, but that has to be pushed.
Okay. Thank you. Okay, a very brief question. Maybe you can set up if you want. Yeah.
On the curvature of your affine submanifold.
It's a good question. It's a good question. I was wondering at some point what is the is there a relationship with minimal curvature stuff? I don't think this is the case, because otherwise it would have been already described. So I think there is something on the curvature, because it seems to be kind of well behaved, and it's kind of the lowest curvature you can have that goes through these 3 points. It doesn't mean that it's I'm not sure that it's a minimal curvature. So that has to be studied.
Okay, thank you.